Okay, let's talk about equilibrium, things that go along with considerations of equilibrium. For starters, equilibrium is the idea that chemical reactions are not a one-way thing. Is that products can turn into reactants, reactants can turn into products. It can go both ways. So given that idea, it may or may not be easy to understand for certain things. This kind of gives a nice little standard. Imagine a water bottle. You look at that water bottle sitting out in the sun. You notice all of this right here. You say, and you probably understand that this is condensation, where the water is inside the bottom. Maybe I'll use a little appropriate blue color here to get the idea across. You got water is evaporating. It's hitting the sides of the bottle, condenses back down, and that's what turns it into this liquid that you see. And eventually, once these droplets get big enough, they run down into the liquid layer. So whatever, you've got this idea of opposite processes proceeding at the same speed. And this is what chemical equilibrium is, when opposite processes happen at the same rate. In this case, the evaporation happens at the same speed as condensation, keeping it in balance, because after all, assuming the cap is on, that water bottle can sit out in the sun all day, all night, forever, and it'll never go dry. Because the gas is nowhere to escape, it's just condensing right back down to water again. So although this is not a chemical process, it is a physical process, and nonetheless gives the idea, the concept, that you can also get by looking at this little cartoon of equilibrium is when one reaction is happening at the same rate as the opposite reaction. You know, as in, like, if you go up the down escalator at the right speed, then steps are going down, you're going up, and you'd be like staying in the same place. So anyway, let's see, okay. So anyway, when it comes to chemical equilibrium, the fact is that, in theory at least, you could reverse any reaction. So consider this one. Sugar can burn. This is glucose sugar. Burning is when it reacts with oxygen, and combustion of a hydrogen-containing compound will make water. Combustion of a carbon-containing compound makes CO2. And, Homer Simpson. But anyway, the idea is then that, wait, this is reversible. You can undo this. And I'd say, yeah. So reversible would mean taking carbon dioxide plus water to make oxygen and glucose, which hopefully that idea is familiar from freshman biology class, because carbon dioxide plus water making oxygen plus glucose, think about that. It's photosynthesis. Plants do that. Okay, so in principle, in theory, any reaction is reversible, where carbon dioxide plus water makes these two things. You flip it around and you're back to having this again. Okay, now some are much faster than others. Like, it takes a tree many, many, many years to grow, and yet it can burn really fast. So, you know, one direction might be far longer and energy intensive than the other, but in principle, any chemical reaction is reversible and can go backwards the other way. So really, you know, it could be more true to look at chemical reactions as two-way things instead of a one-way thing. So weak acids, again, this is not really a chemical change, but when it dissociates in water, you can see kind of the same thing going. So actually, maybe I should back up a little bit. So weak acids can dissociate. That means acid plus water. The acid is a proton donor, gives us proton to water, becoming anion and hydrogen ion, or H3O+. But the thing is, the other side of that, these products can turn back into reactants again. If this one takes a hydrogen off of here, if the hydrogen goes here, it's back to this again. If this loses a hydrogen, it's back to this again. So we put this to show that the reaction can go both ways. Now, with a strong acid, this is also true. It can go both ways, but it's so much weaker. Like, this would be a more correct way to show it. Like, you probably can't even see that we can, for the purpose of our calculations, just ignore it and simplify things. However, for weak acids, the backwards reaction is strong if we cannot ignore it. So we write it like this to show an equilibrium between this and this. Now, when I say equilibrium, what that means is yeah, I had to, okay, is some of these are combining to make this, and some of these are combining to turn back into this again. And it's happening at the same time. They're switching places with each other. They're constantly, this is turning to this turns into this. It's just going, going, going. They're constantly turning into each other. And the amount of this is not changing. The amount of this is not changing in total. The total amount isn't changing, even though individually things are reacting and turning into what's on the other side. Water does the same thing. It goes back and forth between this and this. This really gives an idea of what it is. The total number of things on each side is the same here compared to here, even though atoms and molecules are constantly like switching sides, as in like turning into product, turning into reactant, turning into product, turning into reactant. Although they're moving around, the total number of things over here is always the same. The total number of things over here is always the same. This is what equilibrium is. Equilibrium is when the forward reaction rate equals the reverse reaction rate. Now, if we show a graph with concentration, the lines may intersect with each other, they may not intersect with each other, they may come together, they may not come together, but this is concentration. If it's concentration, not reaction rate that we have on the y-axis, then what we're going to look at is, yeah, at the beginning it's going to be all reactants, no products. All reactants, no products. You'll get more and more product, you'll get less and less reactant left over. But at some point it's going to reach equilibrium where the forward reactions were equal to the reverse reaction. So although these are still turning to this and this is still turning to this, for every one of these that goes here, another one goes here. So you're having like this going on. One of these turns into this, one of these turns into this. That means it is balanced and in equilibrium, and the total amount is not changing, even though individually atoms and molecules are still changing from one form to the other. They're doing it at equal rates, which means it's in balance, and that's what equilibrium is. It's chemical balance. So this is equilibrium because the concentration is no longer changing. This is also equilibrium because the concentration is no longer changing. It doesn't matter if the lines cross or not. That is irrelevant. So in case it's hard to read, at the beginning, only the reactants are present because no product has been made yet. Equilibrium has been reached when concentrations of reactants and products stops changing. All right. So, let's stop there.